Hello, AP Chemistry students. This is Mrs. Altman. We are in video number 32, Acid and Base Equilibria Part 1. We are in Chapter 15 of your textbook. Here are our objectives for today's video. Pause here. All right, I'm going to wait about 5 seconds and then work through it. So in order to understand what's going to happen here, we first need to consider what's actually happening when we have HF in solution. So if I add NaF to this, the fact that it's a solid doesn't really matter because all sodium-containing salts are soluble in water. I'm effectively adding a product. So adding solid NaF will shift the equilibrium to the left as I'm adding a product. Therefore, the pH will increase, meaning getting closer to 7. Pause here. The common ion effect is really just a fancy word for what we just talked about. If you add what's called a common ion, something that really the conjugate base of an acid is typically how you can think about it, it's going to decrease its percent dissociation, which just makes sense based off Le Chatelier's principle. Pause here. So you all are made up of a lot of different things, but one of them being blood. And despite what the claims of many water bottle companies are, the pH of what you eat and drink has nearly no impact on the pH of your blood. And that's because your blood is, amongst other things, a buffered solution. A buffer solution just consists of an acid-base pair that resists changes in pH. So it has to be a weak acid and weak base pair. They must be conjugates of one another. So some examples would be acetic acid and sodium acetate, ammonium, ammonia. Anything that is different just by one proton can be a buffer solution. Pause here. So this is just explaining what buffers do. So let's just say I've got an ammonium, meaning NH4+, and an ammonia buffer, and it's going to resist changes in pH. So the first equation that you see here is what happens when hydroxide reacts with it. So you see that it forms NH3, the conjugate base, and H2O. And then the second one shows what happens when you add an acid to it. The NH3 becomes NH4+, and then it also produces water. Pause here. Okay, I will work through this. So for the first one, I'm adding a strong acid. So it doesn't really matter what it is because I'm really just adding H3O+. This is going to react with the F-, which is the conjugate base. And that will form HF, a weak acid, and H2O. And then for the strong base, again, it doesn't matter which strong base I'm reacting. It's probably sodium hydroxide or something like that. This is going to react with HF, and it will form water as well as F-. Pause here. So let's take a look through these. So the first one is not a buffer solution. And this is because H2SO4 is a strong acid. If H2SO4 were a weak acid, then this would be totally a buffer. This one is a buffer. I've got a weak acid, I've got its conjugate base. The actual concentrations themselves don't matter so much for right now. We'll talk more about them later. And then the third one, you might be tempted to say, no, it's not a buffer because I've got a weak acid, but this one actually is a buffer. And the reason why is that the hydroxide is going to react with the acetate to form sodium acetate. And this is telling me that I'm getting to my limit, so I'm going to end the video here. Thank you so much for watching and have a great night.